Okay, in this video, we will be continuing with Chapter 3 and looking at the derivatives of both products and quotients. Okay, we've looked at several derivative rules, and one of those rules says that the derivative of a sum is the sum of the individual derivatives, and the derivative of a difference is the difference of those individual derivatives. While that is true, we want to see how it translates into talking about products and quotients today in this section. Okay, if we look at this particular example here, we want to consider if we were to take the derivative of product of these versus the product of the derivatives. So looking at this, first of all, if we were to take these two functions and multiply those out, so we'd have to FOIL this out. If we FOIL this out, do first, outer, inner, last, and simplify it, we're going to get this expression here. And we know that the derivative of that expression, the derivative of this would be the 12x, and then the derivative of this would be minus 5, and then the derivative here would be 0. So the derivative of the product of these two functions is 12x minus 5. Okay, but if we want to look at seeing if it's the product of their derivatives, then we want to consider what are the individual derivatives. So the derivative of this is just 3, and the derivative of this is 2. So if we multiply those two together, 3 times 2 is going to be 6. So 6 is clearly not equal to 12x minus 5. So we can't just simply take the derivatives of the individual functions and multiply those together. We have to have a special rule in order to do the derivative of a product of two functions. Okay, so the derivative of a product is not the product of the derivatives. Okay, so in words, what we have is the derivative of the product of two functions is the first function times the derivative of the second plus the second times the derivative of the first. So we're going to look at a couple different representations of this, and you can kind of, figure out which one you like best and latch on to that. Okay, so if our overall function is made up of two different functions, we'll call it capital F for first, capital S for second. So we've got the first function and the second function. Then our product rule says that the derivative of that overall function, so f prime of x, is going to be our first function times the derivative of the second, so s prime, plus the second function times the derivative of the first. So that's one notational way that you'll see it. Kind of in an abbreviated form, it would be f s prime plus s f prime. Keeping in mind the f is for first and s is for second. One thing I will say is because addition is commutative, it doesn't really matter which one of these you have first or second. So those two are kind of interchangeable. This would be another representation with a different notation. So again, first function times the derivative of the second plus the second function times the derivative of the first. Okay, and yet two other representations. This is coming from a different textbook. If you represent your composite function as f times g, then it's going to be f g prime plus g f prime. And then this is one that recently I have seen used that a lot of people really like, and that is if you set up your two functions, f and g, and then you take their derivatives, f prime and g prime, then what you're going to do is you're going to cross this way and multiply the original function times this, or the first function times the derivative of the second, add those together with the second times the derivative of the first. Just a way to keep it organized. All right, so let's see how all this applies. If this is my first function and this is my second function, then by the rule that says f prime of x is equal to f s prime plus s f prime, okay, then our first function is 2x squared And then the derivative of our second function is going to be, the derivative here would be 4 times 3 would be 12x to the third. The derivative of minus 4 is 0. Okay. Then we're going to put plus the second function. And then we're going to have the derivative of the first, which would be 4x. Okay. So we can simplify that. The main thing here that I'm going to be looking for is that you have all the pieces of the derivative. Simplification in a lot of cases will earn you an extra couple points, but it's not going to cause you to lose points if you don't do that. So these can multiply together and give us 24x to the fifth. And then if you distribute here, you're going to have 12x to the fifth minus 16x. And we could combine these together as like terms and have 36x to the fifth minus 16x. So that would be using this approach here to this particular function. If I wanted to use what I'm going to call the box method, so with the box method, you set it up and you have your two functions, so your first function and your second function. And then we know we're going to have the derivative, so we're going to go ahead and take the derivative of each one. So the derivative of this would be 4x. The derivative of this would be 12x to the third. So then we're going to cross this way. So 2x squared times 12x to the third plus, and then we're going to cross back this way. And you can see that we have exactly the same thing that we had here. So it's just a different approach to it, but it's going to get you to the same place. And actually, yet another approach for this particular one would simply be, instead of taking the derivative as a product, you could have multiplied this one out first and then take the derivative of this. So you would have, if you multiply that out, you would have 6x squared minus 8x, 6x to the 6th minus 8x squared. But if you took the derivative here, you'd have 36x to the 5th minus 16x. And that's what we ended up with the other way. So sometimes it's simpler just go ahead and multiply it out and then go back to our basic rules for derivatives. All right, so here's one you may take an opportunity to practice with, or just stay with me on this. So we've got the first and our second function. So you could either multiply it out and then take the derivative, or set it up and do first and second. Okay, so the derivative here, 3 times 3 is going to be 9x squared. The derivative of this will be 4x minus 3. So we're going to multiply this way, add, and then go this way. So 3x to the third. Okay, so 3x to the third times 4x minus 3. So going down this direction. Plus, now we're going to go up this way. So 2x squared minus 3x plus 1 times 9x squared. So here we've got all the parts of the derivative. If you did, this will be first times the derivative of the second plus the second times the derivative of the first. And it's just a matter of simplifying by distributing. So if I distribute here, I'm going to have 12x to the fourth minus 9x to the third plus distribute here to each term would be 18x to the fourth minus 27x to the third plus 9x squared. And we do have some like terms here, so that's going to give us 30x to the fourth. We've got some more like terms, so minus 36x to the third, and then plus our 9x squared, and that will finish it up. All right, if we look at this one, again, you could set it up with the box or the first and second. Okay, so here, if I'm doing my derivative would be the first. So I'm just recopying the first. And then I'm going to follow it by the derivative of the second. So 3x squared plus the second. And then I'm going to times it by the derivative of the first, which would be 4x. So that has all the parts of the derivative, I just need to simplify it by distributing. So 3x squared times 2x squared will be 6x to the fourth. 3x squared times minus 1 will be minus 3x squared. Here we'll distribute also, and we'll have 4x to the fourth plus 12x. We do have a pair of like terms, and so we'll have 10x to the fourth minus 3x squared plus 12x. And you can kind of see if you wanted to do it in the box, this is kind of what we're looking at here. You've got your two functions of the derivatives, add them together once you've multiplied. Okay, here's some to practice. This one actually probably would be easier to go ahead and multiply it out. So if I multiply this out, it'll be 6x to the third minus 42x squared. So then the derivative is going to be 18x squared minus 84x. And you could definitely have done first and second. So you do first times the derivative of the second plus the second times the derivative of the first. All right, if we look at this one, if we do our functions and our derivatives, and I'm just trying to show different techniques so you get an idea of which works for you. So our first function is 2x to the fourth plus 3. The second is 3x squared minus 4. Their derivatives here, that derivative is going to be 8x to the third. Here it's going to be 6x. And that's just going back to our power rules and our constant multiples. Okay, so it'll multiply going this way. So the first times the derivative of the second plus the second times the derivative of the first. And if you get in the habit of kind of saying these rules in your head, I actually think it does make a lot of make it a lot easier to remember. Okay, we'll distribute here, so 12x to the fifth plus 18x. Distribute here, so I have 24x to the fifth minus 32x to the third. Okay, combine our like terms together. So I've got some x to the fifth. That'll give us 36x to the fifth minus 32x to the third plus 18x. Okay, so again, we've got your first and your second. So this will be my first, second. So the derivative then, and keep track of your notation. So once you're actually taking the derivative, call it the derivative with the prime sign. So here, our first function, and the derivative of this second function is going to be just 2x. And then we're going to have the second function, and we're going to multiply that times the derivative of the first. So the derivative of this is going to be 3x squared plus 2. Okay, so to clean this up, we're going to distribute. Here we're going to FOIL because we've got two binomials. So when I FOIL, I'll have 21x squared for my first term, my outer term, my inner term, and then my last term. Okay, so we do need to check for like terms here. So I have a 3x to the fifth. Oh, and I copied this wrong. This should have been a 2 here. Okay, so that's actually going to change a couple of our terms here. It's going to change this to being 3x to the fourth, and then this will be 2x squared. So when I combine like terms, I do have some common terms to combine together. So I'm going to have 5x to the fourth, and then with the x squared, I'm going to have 4, 21, and 2. So that's going to give me 27x squared. And then I'm going to have an 8x and a 14. Okay, looking at this one here, we've got our first and our second. Okay, so especially as you get more complicated with the functions, I think maybe the box might be the easier way to go with this. Okay, so this would be 1 plus, I'm going to write this as t to the 1/2 because when we're taking derivatives, we know that we're going to have to get rid of that radical before we can do anything. Then the second function is 8t squared minus 5. So if I look just specifically at this derivative, the derivative of 1 is 0. The derivative here is going to be 1/2 t to the negative 1/2. And then the derivative here would be 16t. So we're going to multiply this way and then multiply this way. So we'll have the first times the derivative of the second plus the second function times the derivative of the first. And I'm really not that concerned about a lot of simplification here. If you wanted to distribute, you'd have 16t plus 16t to the 3/2 because you'd add those exponents together. Here, if you're distributing, 8 times 1/2 would be 4t, add your exponent, so that would be to the 3/2, and then minus 5/2 t to the negative 1/2. So we do have a set of like terms there, so we'll have 16t plus 20t to the 3/2 minus 5 over 2t to the 1/2. Okay, but as far as like having full credit, as long as you get to this point here, then that would be sufficient. All right, these product rules will also translate into problems that have exponential and logarithmic functions. So, like on this, when you see something like this, you have to start identifying what are the two functions that are being multiplied together. So we're going to let this be the first, and this will be our second function. So we're going to go, our derivative is the first times the derivative of the second plus the second times the derivative of the first. Okay, so the first is 5x to the 8. The second, the derivative of the second, the derivative of e to the x is just e to the x. And then here the second also happens to be just e to the x. And then the derivative of the first would be 40x to the 7th. Okay, we can clean this up a little bit because there's actually e to the x's in both terms. We can pull that out. And there's also a factor of 5. And we'll move over a little bit here. So I could pull out a 5 as a GCF. I could pull out an x to the 7th. And I could take out an e to the x. And that would leave me with an x and then plus 40. All right, this next one, we'll let this be our first function and this be our second function. And again, just to show different ways to do these, if I set up my function and then my derivative, my first function we said is x to the 7th, and the second one is the natural log of x. So I think the good thing about this is it lets you just focus on that and not like the whole combination of it. So if I have x to the 7th, the derivative would be 7x to the 6th. If I have natural log of x, the derivative would be 1 over x. So we don't have to get confused with something too complicated at this particular point. All right, we're going to crisscross here. So we'll do the first times the derivative of the second plus the second, which is natural log of x, times the derivative of the first. Okay, when I multiply these together, I'm going to get x to the 6th, and then here, there's really not much I can do. I'll just rewrite it like this, and that's going to be our final answer. If you wanted to take out an x to the 6th, since we do have that in common, you could write it like this. Okay, moving on to the quotient rule. So the quotient rule is a little bit more complicated than the product rule, but the main thing is like just understand the rule and the different parts and you should be fine. So just to kind of explain, like the derivative of the quotient is not the quotient of their derivative. So you do, when you are dividing things, you have to have a special rule for that. So here, instead of calling it first and second, we're going to call it top and bottom. Okay, so with the derivative for this one, it's always the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. There's different representations, so we'll look at other ways for you to remember this. Okay, so that's the one we just looked at. This would be kind of the simplified notation. So bottom times the derivative of top minus top times the derivative of the bottom over the bottom squared. So it's always the bottom squared that's in the denominator. And with the quotient, it's subtraction, not addition. And so because of subtraction, it does matter which one you start with. So you're always going to start with the bottom times the derivative of the top minus the top times the derivative of the bottom. So getting that order right is super important. Okay, if you want to think of it in terms of F and G, this is another representation that you could use. This is kind of it written out in words. So if you want, if that helps you, then that's a representation for you. Here's a couple little, like, almost like sing-alongs. You've got, with the quotient rule, you've got low, D, high. So D meaning derivative. So the lower one times the derivative of the upper one minus the upper one times the derivative of the lower one over the lower of two lowers, or low D high minus high D low over low low, or low D high minus high D low over the square of what's below. So, like whatever works for you, go with it. That's the thing to remember it. All right, so if we're looking at this example here, okay, so we're going to have, this is our top and our bottom. So the derivative here is going to be the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. Okay, so the bottom is 2x minus 1. So we're going to have 2x minus 1 times the derivative of the top, which is 2x, always the subtraction sign. And then we're going to do the top, and we're going to follow that by the derivative of the bottom, which in this case is just 2. And then that's going to be over the denominator, or the bottom squared. Okay, so generally you're only going to simplify the numerator part of this. So that's going to be 4x squared minus 2x. And then here this is going to be minus 2x squared. Don't try to multiply the bottom out, just leave it like it is. So you'll have 2x squared minus 2x over 2x minus 1 squared. All right, so we're going to look at a couple other representations here. So this again would be the top and the bottom. If you wanted to do this with the chart, like we looked at for the product rule, then you're going to have your function and you're going to have your derivative. Okay, so my two functions are 2x and x squared plus 3. The derivative is 2 and 2x. Okay, the thing with this is, because the rule says we have to start with the bottom, you're going to have to, you start, before with the product rule, you started from the top. With the quotient rule, you start from the bottom and multiply. So it's going to be the bottom times the derivative of the top minus, remember you have to do minus for the quotient rule, then go down this way, minus the top times the derivative of the bottom over the bottom squared. So you can still use a representation of that. It just changes slightly. Okay, so if we simplify this, we're going to have 2x squared plus 6 minus 4x squared over the denominator squared. So negative 2x squared plus 6 over x squared plus 3 squared. All right, so a little more complicated, not terribly, but we'll let this, I mean, this is our top, this is our bottom. So if we're going to find the derivative, we're going to do bottom times the derivative of top minus top times the derivative of the bottom over the bottom squared. Okay, so our bottom is t squared minus 4, and the derivative of the top would be 3t squared minus 3 minus, because it's the quotient rule, and then we're going to have the top, and we're going to have the derivative of the bottom, and then all of that is going to be over the bottom squared. So there are times it's probably possibly not worth our effort to simplify, because like this one we'd need to full because we've got two binomials. So we would have 3t to the 4th would be our first, our outer, our inner, and our last. And then over here we're going to distribute. So minus 2t to the 4th, and then plus 6t squared. And it's a plus because I've got one negative here and another negative here. So the two combine together to give me a plus 6t squared. All that is over this denominator squared. Okay, if we try to simplify this a little bit, the numerator, we've got some like terms, the t to the 4th. Okay, we'll be left with 1t to the 4th, and then we've got, these will be negative 15t squared plus 6 will give me a negative 9t squared, and then I have the plus 12, and all of that is over t squared minus 4 squared. Okay, so again, to get full credit for the derivative, you just need to be here. If you want to try for the bonus point, then you're going to need to be able to simplify it. Okay, if we've got this and we're asked to find the derivative in two ways, okay, one way would be the quotient rule, okay, and can't spell the quotient rule, okay, and the second way is going to be the bunny ears. Okay, so the quotient rule says that we would do, we would have our top and the bottom, so it's going to be the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. Okay, so that would be 3x, add your exponents, so 3x to the 5th minus 2 times 3 is going to be 6x to the 5th. Actually, 6x to the 2nd. And then minus 3x to the 5th. And then that's going to be over x to the 6th, because we'll multiply the exponents here. And this negative, we do need to make sure it's distributed through to both terms so that both of those are negative there. Okay, so these actually cancel, and we're left with negative 6 over x to the 4th. Okay, so that's using the quotient rule. If we use the bunny ears tells us to simplify it first. Okay, so if I'm going to simplify it first, I'm going to have 2 over x to the 3rd plus x to the 3rd over x to the 3rd. Okay, so this is 2x to the negative 3 and then plus 1. So all that is just rewriting it. Now if we take the derivative, this is going to give me negative 3 times 2 will be negative 6x to the negative 4. The derivative of 1 is 0, so we end up with negative 6 over x to the 4th. So you can see in this particular case, the bunny ears was probably a simpler way to do this than the quotient rule. So generally, if you can rewrite it so that you don't have to use the quotient rule, that's going to be to your advantage. All right, here's one to try. So I'm going to do kind of the box with the function and the derivative for this one. Again, just to give you different techniques. So our first function is t squared minus t, and the second is t to the third plus 1. The derivative of this would be 2t minus 1. The derivative here is going to be 3t squared. So if you're going to do it with kind of setting it up in these columns here, you always have to start with the bottom when you're doing the quotient. So we're going to have the bottom times the derivative of the top minus, and then we're going to go the other direction, t squared minus t times 3t squared, and then that's going to be over t to the third plus 1 squared. I'm not going to go into simplifying it because, like I said, the focus really is on getting the pieces of the derivative. You would need to FOIL here, and you would need to distribute here. Okay, so you can see it's still pretty complicated. Okay, so if we let this be top and bottom, so our derivative for this one, we're going to have the bottom times the derivative of the top minus the top times the derivative of the bottom, which is just e to the x. And then that's going to be over e to the x plus 2, and that whole thing squared. Okay. If we wanted to simplify, we'd need to not full, distribute here. So 3x squared e to the x, 6x squared, and then here it'll be minus x to the third e to the x. So we don't have any like terms to do anything with. So we're just going to leave it like that. Okay, this one, if we do our top and bottom, then the derivative, again, use your notation to indicate that you are now taking the derivative. So the derivative is going to be the bottom times the derivative of the top minus the top times the derivative of the bottom. So the derivative of the bottom is going to be 0 for this and 1 over x. And then that's all going to be over the denominator squared. Okay, so if I wanted to distribute here, I'll have 4 plus 4 natural log of x. And then these are going to simplify to be just minus 4. The x's would cancel. Those 4's are also going to cancel. So 4 natural log of x over 1 plus the natural log of x. I have a business application. So the total sales S represented in thousands of games of a video game T months after the game is introduced is given by this particular equation. We want to find the derivative. Okay, so the first one is not really that much of an application. Literally just applying the quotient rule here because we are dividing two things, so it would require the quotient rule. So our derivative then is going to be the bottom times the derivative of the top, so 250t, minus, because it's the quotient rule, the top times the derivative of the bottom, and then all that over the bottom squared. Okay, if we simplify here, we're distributing, so we'll have 250t to the third plus 25,000t minus 250t to the third, and then all of it's going to be over this. So what you can see is we get, and this happens, a fair amount of the time, you get that cancellation there. Okay, so we get 25,000 t over t squared plus 100 and that whole quantity squared. So that's going to be our derivative. Okay, so we want to find s of 10 and s prime of 10. So I really want you to focus on what these are asking you to do. So this one, because it's just s function, is saying go to the s function, plug 10 in for the t. Okay, so if I do that, I'm going to put 10 in everywhere I see a t. So when I do that, I'm going to get 62.5. Okay, so s represents the sales, and that's in thousands of games, and T represents the months. So basically, this is the sales after 10 months, the total sales after 10 months. So this would be 62,500, and that's in video games. Okay, so 62,500 video games have been sold in 10 months. Okay, if we look at s prime of 10, so obviously we need to go to the derivative and plug in 10. That's what that notation tells me to do. So going back to that derivative that we came up with, it was 25,000 t over t squared plus 100 and that whole thing squared. So if I plug 10 in the place of the t, then I'm going to get 6.25. Okay, so 6.25 is no longer the total sales, it's how the total sales are changing because it's the derivative that we're talking about. So it's the total sales are changing. Okay, and since this is positive, that change is increasing. So total sales are increasing by 6.25, and this is in 1,000 video games. And since our time unit is months, it's going to be per month. Okay, and we're going to look at like a more polished version of that. But the main things you need to be able to tell me is that it's the sales that are increasing, and it's like a per month unit there. So sales are increasing at a rate of, and they just converted this to thousands, so 6,250 games per month. Okay, so if we want to estimate the total sales after 11 months, okay, so we found out that the first 10 months, our total sales were 62,500, and we also found that at that point they're changing at about 6,250 per month. So this would represent 10 months. This represents one additional month. So if I combine those together, this is going to give me the total number of games at the 11th, after the 11th month. And again, that's an estimate. I could plug in 11 into the actual function, and that's going to give me like the actual number of sales after 11 months. All right, so on this one, we're going to basically go through the same thing here. We need to find the derivative. So the derivative, we've got top and bottom. So our derivative is going to be t plus 3, so bottom times the derivative of the top plus the top times the derivative of the bottom. So the derivative of the bottom is just 1, and we'll divide that by the bottom squared. Okay, so if I distribute here, I'm going to have 150 plus 150t plus 450, and then actually I have a mistake here. This needs to be, since it's a quotient, it does need to be subtraction. So we're going to subtract the 150t. Okay, so those are going to cancel, and we're going to have 450 over t plus 3 squared. Okay, so we want to find s of 12 and s prime of 12. So this tells me go to the original s function and plug 12 into it. So s of 12 is going to be 150 times 12 over 12 plus 3. So that will be 120. This is asking me to go to the derivative and plug 12 in it. Okay, so we found that the derivative was 450 over t plus 3 and that whole thing squared. So in the place of the t, I'm going to put 12. So 450 over 15 squared is going to give me 2. Okay, so just kind of so you can see the written out version of it, as far as the interpretation, because we're plugging 12 in for the T, that is going to be the total sales after 12 months. So 12 months after the video game is introduced, the total sales are 120, and our units was 1,000, so 120,000 video games. When we plug the 12 into the derivative and get 2, that's the derivative tells me the rate of change, like how fast the sales are changing. Since it's positive, they're increasing. So at the point of 12 months after the game is introduced, because it's always relative to a specific time, 12 months after the video game is introduced, the sales are increasing because we had a positive number at a rate of 2, and again, that was in thousands for our units. So 2,000 video games per month because our time was measured in months. And then as far as estimating the total sales after 13 months, that's just going to be going back to our the 120,000 for the 12 months, and then the other 2,000 that would be for the rate of change for each additional month. So we'd look like we would have 122,000 video games being sold. Okay, we always have these tangent line problems and they don't really go away, but the one reason we keep looking at them is to help you understand the process with this. So anytime we're going to write the equation of a tangent line, I need a point and I need a slope. Okay, so the point will always come from my original function. The slope is always going to come from the derivative. Okay, well, I have my original function here, so I really just need to find the derivative. Okay, so this is two things multiplied together, so this is a product rule. So I'm going to do the first times the derivative of the second plus the second times the derivative of the first. Okay, simplified if it could be simplified easily. So this will be 4x squared minus 18x. This will be 2x squared plus 12. Okay. All right, we need to figure out what our point actually is, and they want us to look at it when x is 3. So I'm going to figure out what f of 3 is and what the derivative at 3 is. So I'm going to plug 3 in here. Okay, so that's going to be 6 minus 9 would be negative 3. Here it's going to be 9 plus 6 will be 15. So it looks like negative 45. Okay, when I plug into the derivative, I'll have 4 times 3 squared minus 18 times 3 plus 2 times 3 squared plus 12. And that looks like it's going to give me a value of 12. Okay, so our point then is 3, negative 45, and our slope is 12. So I just go to my y equals mx plus b and plug everything in. So negative 45 is equal to 12 times 3 plus b. So this will be 36. So b is going to be, looks like negative 81. So I have y equals 12x minus 81. All right, find the values of x where the tangent line is horizontal. So that is going to be where our derivative is equal to 0. So we found earlier that our derivative is equal to 6x squared minus 18x plus 12. And that would be if we were to combine these together, so 6x squared minus 18x plus 12. Okay, so that means in order to find where the tangent line is horizontal, that's going to be where that derivative is equal to 0. So the easiest way to do this is to see if we have a GCF, and we do have 6 as a GCF. So by taking that out, it actually gives us a trinomial that's pretty easy to factor. So we need, what, two numbers that multiply to give us 2 and add to give us 3. So that's going to be -2 and -1. So we'll set each factor equal to 0. We don't really get anything when we set 6 equal to 0, but if we set these equal to 0, we're going to get 2 and 1. So those are the two values of x where our tangent line is horizontal. Okay, so here's one to practice just like we just got finished doing. So you need to figure out what f of, in this case, 3 is and f prime of 3 is. So we need to find the derivative here. Okay, so that's going to be the first times the derivative of the second plus the second times the derivative of the first. Okay, so 4x squared plus 18x plus 2x squared minus 24. That's going to give me 6x squared plus 18x minus 24 for the derivative. Okay, if I plug 3 in up here, if I put 3 in this, it's going to be 6 plus 9 will be 15. And then if I put 3 in here, that's going to be 9 minus 12 will be -3. So I'm going to get -45. And if I put 3 into the derivative, I'm going to have 6 times 9 plus 18 times 3 minus 24. And that's going to give me, looks like 84. So that would be my m. So then I'll do y equals mx plus b. My y is -45. My m is 84 and my x is 3. Okay, so this will be a positive, and then b is going to be, if I put these together, it'll be -297. So my equation is going to be y equals 84x minus 297. So that answers part A. Part B, where is the tangent line horizontal? That's where the derivative is going to be equal to 0. So I want to take the derivative that I found here and set that equal to 0. So I'll factor out my GCF. And then again, this is going to factor pretty easily. Two numbers that multiply to give me 4 and subtract to give me 3 will be +4 and -1. So if I set each factor equal to 0, I'm going to get -4 and 1.